Does anybody have any homework questions? I had asked you on Friday to start thinking about infinity. So hopefully you did think about infinity. The question that the author suggests we open with is, what comes to mind when you think about infinity? Let me just see if I can get this. Here we go. What comes to mind when you hear the word infinity? Write your thoughts or questions on a piece of paper, please. Okay, so what comes to mind when you hear the word infinity? Can you write down what you think about? I almost forgot to suggest that you print the review. So on Wednesday we'll go over the review. It'll be easier if you have it printed. You can do it from your iPad or your phone. But if you have it printed out, then of course you can write on it. So if you want to print out the review and bring it to class on Wednesday, that would be helpful, because that's what we'll do on Wednesday, is review for the quiz on Friday. Well, we are thinking about what comes to mind when you hear infinity, and I'd like to hear what some of your ideas are. Who would like to share what comes to mind when you think about infinity? Yes?
Forever.
Forever. So time going on and on forever. Infinite time. What other things do you think about? Yes?
Like space and the universe.
Has anybody taken astronomy? I think they say that space goes on forever. Yes, so that's what you were thinking too, right? Okay. Anything else that comes to mind when you think about infinity? Yes?
Never ending.
Never ending. Yes?
The symbol for it.
The symbol.
The snake that repeats it.
The sideways H, right? Is that what you meant?
Yeah.
Okay. Anything else? It's not even clear if infinity belongs in the mathematical realm. Maybe it belongs in the religious realm, or philosophical, or literary. Your author says it's one of the great triumphs of the human intellect that this vast idea, which seems enormous and overwhelming, is able to be subject to the human intellect. And to, how does he phrase it? To tame it and make it susceptible to reason. The life lesson in this section is to understand simple things deeply. So before we tackle infinity, we think about finite. So before we tackle something so vast and huge as infinity, we'll talk about the finite. And in math, we talk about the finite in context of sets. So sets is another word for a collection of things. Can anybody think of some examples of finite sets that are actually in the room, in this room? Yes.
Speakers.
The speakers?
There's only a certain amount of speakers in the room, or.
Do you mean the electronic speakers?
Sure. Or the amount of ink in all these markers.
Okay.
It's all finite. Soon will run out.
Okay. So the amount of ink in the markers. And I'll put that in little braces. Those little braces in math mean the set of. So that means the set of the amount of ink in the markers. Or the set of the speakers in the classroom. I was thinking microphones when you said speakers, because there is no microphone. I have to bring a microphone from each time. But yes, I see there are speakers, yes. What are some other examples of finite sets in the classroom here? I should have you each write one down. Okay, so each of you write one down, and then I'm going to call on a few of you, okay? Finite sets. Okay, so now I'll come around and ask you. Okay, so what did you write? Look around you. See any items you like. Computers. Okay, the number of computers in the classroom. Okay, and I'll go pick somebody else, unless somebody raises their hand. Yes. Number of people in the classroom. Okay. And what would be another set of finite? Yes?
Number of pencils.
The number of pencils in the classroom. Well, you folks are putting your minds to it. I can see that. So this would all be a finite collection of sets. Well, we're going to be comparing some of these sets. Okay, so let's think about shoes. So we have a set of shoes in this room, and let's compare it to the set of feet in this room. Do they have to be the same size? No. I see head shaking, no. So how could we tell which one's bigger? We could ask a few questions, right? Okay. Does anybody have an extra pair of shoes in their, along with them, like in their backpack? Anybody have an extra pair of shoes? No extra pairs of shoes. Is there anybody not wearing shoes? Okay, we're all happy to know that. Okay, so what would we say about the sizes of these two sets then?
Equal.
Yeah, they're equal. Okay, how about if we take the people in this classroom, one of our sets up here, and compare it to the number of computers in this classroom. So we could ask the same kinds of questions, right, to help us compare those size sets. I can count this as my computer. Did anybody bring two computers? Anybody bring two computers? We won't. You brought two computers? Okay. Your what?
iPad.
Yes, we'll count tablets as computers, but let's not count cell phones. We'll do that one next. Okay, cell phones next. Okay, so you have 2. Did anybody not bring a computer or iPad? So, is there anyone here who doesn't have a computer or iPad? Oh, that's interesting. I didn't. You don't? Okay, okay. With the light behind you, it's hard for me to see. Okay, so 1 person? Or is there anybody else besides you? Okay, but then you have 2. So now what can we say about the size of the sets of number of people in the classroom and computers in the classroom? They are the same. They're the same because 1 person didn't bring 1, but then 1 person brought 2. So these are the same size also. How about, let's do the people in the classroom and cell phones. That'll be a little less ambiguous. I didn't bring a cell phone. Did anybody else not bring a cell phone? You didn't bring a cell phone? Okay, so 2 people didn't bring cell phones. Did anybody bring extra cell phones? More than 1 cell phone? Okay, so what do you say about these 2 size sets then? They're not equal. No. This is larger. And this one's smaller. I don't know what that symbol means. I'm trying to say this one's larger. I'll just use an arrow. That makes more sense. Well, I have some other sets. I have some sets of squares that I cut up here. There's purple squares and pink squares. How can I tell if the set of purple squares is larger than the set of pink squares, or the set of pink squares is larger than the set of purple squares? You can count them, yes. Okay, I don't like to count things because a lot of times I'll be counting and people will start talking and then I'll be all goofed up. So if I don't want to count, is there another way that I can figure out?
Weight.
What's that? Weight? That's a second way. You could weigh them. So at home I have a scale that weighs in grams, and that would work perfectly. I don't have that here though.
Could you just group them without counting and seeing how many don't fit in the group?
Okay.
If there's one left over.
Yeah, so we could group them without counting and see how many don't fit in a group, because then I don't have to count and I can keep talking at the same time. And that's kind of what we were doing with the shoes and the computers too. We were just trying to match up one of each together. So that's what I'll do here. Whoops, that didn't work. I know you're waiting with bated breath, right? Because it's going to be, and then they are the same. So they are the same size sets, and we can find that out by matching them up. When we match up like that, what we're doing is a one-to-one correspondence. So let's go ahead and write that down. You can call that a one-to-one correspondence or one-to-one pairing, where you match up one element from each set together. And they're one-to-one because there's no extra elements in either set. Each is used. Each is matched with one other. And only one other. So a one-to-one pairing could be made with your fingers from one hand to the other. Okay, you could take your fingers and pair them up. So you have one finger from each hand. So I have the same fingers on each hand. They're in a one-to-one pairing or a one-to-one correspondence. I'll use the word pairing and correspondence interchangeably. Well, we have been using sets that are made up of real objects. In math, we make up sets with numbers and letters and such so that we can make comparisons. So that's what we're going to do next. You know what, I think before we do that, I'll ask you a few questions like you might see on a quiz though. Is there a one-to-one correspondence between the students? Here, let's use set notation, okay? The students in this classroom is there a one-to-one correspondence between the students in this classroom and the noses in this classroom? There's actually a mathematician in your textbook who does not have a nose. He lost it during World War II. Mandelbrot was his name. Okay, but we all are in that situation. Okay. So what did you answer?
Yes.
Almost. This was a trick question. I have a nose too, and I'm not a student. So the answer is no, because I have a nose. So it was kind of a trick. Let's try another one. Is there a one-to-one correspondence? Let's just call that A, and then we can not write is there a one-to-one correspondence down again. Okay, so B, is there a one-to-one correspondence between people in the classroom? So now we have people. And faces in the classroom. Is there a one-to-one correspondence between people in the classroom and faces in the classroom? So go ahead and write down the answer, please. What did you write there? Yes, yes, yes. That one's yes. One face with each person in the classroom. Okay, here's another one. Is there a one-to-one correspondence between... Boy, I had a good one. Where did it go? Feet in the classroom and people in the classroom. Is there a one-to-one correspondence between feet in the classroom and people in the classroom? Correct. It's no, because the people have 2 feet in general. Okay. Well, these are just where we're thinking of the one-to-one correspondence, but we're not actually mapping it out. We like to be able to map out the correspondences, and that's why we can write sets out to do that. So let's do an example of that. So we're going to actually make a one-to-one correspondence. Whoops, I'm going to say if possible. Make a one-to-one correspondence if possible And then we'll just enumerate a few sets here. So in the first example, we'll have the set T made up of the numbers 1, 2, 3, 4, 5. So we actually tell the elements in the set. The numbers 1, 2, 3, 4, and 5. And the set W, which is the letters A, B, C, D, and E. So to make a one-to-one correspondence, we're just showing the matching up, and you can use little arrows to do that. So you want one element from T to go with one element of W. Every element used up, none used twice. So that's pretty easy. I drew the elements mapping corresponding to one another just vertically, but you could make your arrows go all over just so one number goes to one letter and they're all used up. And none are used twice. Here's another example. This time we have the set M, which is 1, 2, 3, 4, 5. And the set X, which is the days of the week. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So this one, could you make a one-to-one correspondence? No. There's no way, because there's 7 days in the week and we only have 5 numbers. So this one is impossible. Impossible to make a one-to-one correspondence there. So we say that two sets have exactly the same number. No. I said have and I should have said are. Two sets are exactly. Sorry about that. Are exactly the same size if and only if their elements can be put into a one-to-one pairing. Two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing. Now this seems kind of simple with finite sets, but we're going to be looking at infinite sets. So it's going to get a little more confusing. In fact, the first person to bring us set theory, which is what we're looking at when we study the infinite in terms of sets, the first person to bring us a good explanation of what was going on when we studied infinite sets was George Cantor. And because his ideas were so new and raised so many new ideas, the mathematicians of his time just really were hard on him as they critiqued him and blasted his work, which now, I mean, that went on for decades. They were so mean to him that he spent much of his later years in an insane asylum. He had a nervous breakdown. It was just too much. But now his ideas are accepted as the basis of set theories. So because his ideas hinge on this idea, two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing, and because that can get complicated with infinity, I want you all to raise your right hand and repeat after me what we just wrote, okay? Okay. Two sets are exactly the same. Okay, say it with me. Two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing. So help me God. No, I'm just kidding. Okay. So that's what you're supposed to upload to D2L. So take out your phone, or you can just type it in the comment section in D2L, and we'll go on to section 3.2 while you get that going. So you can either take a photo of that we just read, or you can type it in. Now this section starts with how much bigger is the set of rational numbers than the set of natural numbers? How many fractions are there between 0 and 1? So we're going to come back to that question before this section is finished and answer it. We won't finish this section today. We'll just get a start on it. So we're looking at section 3.2. We looked at finite sets already. And we're going to look at infinite sets as well. Now with finite sets, I'd like you to think about what is the smallest. What is the smallest possible number of elements in a set? For a finite set, what is the smallest possible number of elements in a set? Yes?
2.
2. Okay. So like 2 is a set like that, right? So you have the number 1 and the number 2. Okay. So that is a very small set indeed. Are there any smaller sets? I think you went to 2 because you thought like 1 is a lonely number, right? It's the loneliest number of all. In fact, I bet you thought there was a song about it, right? So yeah, you can have a set with just 1 element. Are there any smaller sets than that? Did anybody ever talk to you about the empty set? The empty set, so it's just the braces, there's nothing in there. Empty. Sometimes people designate the empty set with a 0 with a crosshatch through it. Or a slash through it. Okay, so you could have 0 in your elements, 1 element, 2 elements. So actually the smallest set of all has no elements in it. It's the empty set. Let's define a finite set. A non-empty set. A non-empty set is finite if there is a natural number n. A non-empty set is finite if there is a natural number n such that there is a one-to-one pairing between the set and the set A non-empty set is finite if there is a natural number n such that there is a one-to-one pairing between the set and the set 1, comma 2, 3, 4, comma dot 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 n. So we saw some examples of that in 3.1, right? We saw here this set W was finite. We put it in a pairing with the set 1 through 5. So 5 would have been the number n there. Let's look at another example. We'll let the set S equal the alphabet letters up through say L. And we'd say set S is finite because S can be put into a one-to-one pairing with the numbers 1 through however many letters we have here. I think I counted 12. So in other words, you can count those numbers, right? You can count the letters. If you can count the letters, you can put them in a one-to-one pairing with the numbers 1 through whatever your count came to. So just pair them up. Whoops. Yeah. Okay. So the little arrows indicate how you're pairing them up. And you wouldn't have to pair them in order, but it's certainly easier not to miss any or use any twice. Well, now that we know what a set is, that it's finite, a set is finite if it can be put into a one-to-one pairing with the set of natural numbers up through n. A set that can't have that done is infinite. Okay, so a non-empty set that is not finite is infinite. Let's write that down. A non-empty set that is not finite is infinite. Well, how about you tell me some sets that you would think are infinite? So some examples of infinite sets. So examples of infinite sets.
Natural numbers.
The natural numbers. Okay, wonderful, the natural numbers. So the natural numbers, those are the numbers that go 1, 2, 3, 4, comma, dot, 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 forever. We'll be talking a lot about the natural numbers through the chapter 3, so let's go ahead and give them their abbreviated name, which is n with a double bar like that. So then you don't have to write down the set of natural numbers. You can just write, or even the natural numbers, you can just write that n with a double bar. So the assertion is that the natural numbers are infinite. Let's prove it. Prove the set of natural numbers is infinite. So we've looked at a couple of proofs this semester. Our proofs have to be an unassailable line of reasoning. Each statement we make must be effective and unable to be contradicted. So let's make a proof to prove that the set of natural numbers is infinite. What would be one way to prove that?
Find the largest natural number.
Okay, so that's a good starting point. So if they're not infinite, there is a largest natural number. Okay, so you're using a
To see if there is one, yeah.
yeah. So let's assume there is one. So suppose there is a largest natural number n. Okay, so we're assuming the opposite is true. We did that once with the proof for the square root of 2 to show that the square root of 2 was irrational. We first assumed that it was rational. We assumed the opposite. So assume the opposite. Assume there is a largest natural number n. Okay, what's the problem with that?
It stops.
It does stop. And what happens what really happens?
Just keeps going.
It just keeps going. Yeah, it does. It keeps going. In fact, what would the next number bigger than that be?
One bigger than that.
One bigger, yeah. So, okay. So that's what we'll say. So you can assume there is a natural number n, that's the largest. But that brings you to the next one, n plus 1. That's a bit larger. So that's a contradiction. And that we only had one step of reasoning, which was correct, that the n plus 1 is larger than the n. And so that means the original assumption is wrong. Okay, so good. Very nicely done. So we assume that there was a largest natural number n, but n plus 1 is larger, and that's a contradiction. So the assumption that there is a largest natural number is wrong, and we've proved that the natural numbers are in fact infinite. This is as far as we got in the first class because we had some technical difficulties, and so I'll say this is as far as we'll go here as well, so you can keep the two classes together. Wednesday we'll be reviewing. If you have any questions, you can ask the class.
We get a note card for the quiz, right?
You do get a note card for the quiz, so you might want to be thinking about what to put on it,
Oh, front and back?
front and back.